Stationary solutions of the 2D Euler equations in a disk exhibit a striking symmetry property. Specifically, a steady flow with a single stagnation point and tangential boundary conditions must be circular, as conjectured by Hamel and N. Nadirashvili. The proof relies on local symmetry properties of non-negative solutions to semilinear elliptic equations with continuous nonlinearities in a ball. This is achieved through continuous Steiner symmetrization, a powerful rearrangement technique. By exploring how domain geometry influences steady flow properties, the authors identify conditions under which solutions inherit geometric symmetry properties from the domain. This groundbreaking work sheds light on the intricate relationships between fluid dynamics and domain geometry, significantly advancing our understanding of steady flows in diverse domains. The research paper discusses the fluid dynamics problem of a two-dimensional incompressible fluid with a vorticity function dependent on the stream function. It focuses on a conjecture by Wang and Zhan, stating that if there's only one stagnation point, it must be the origin, and the flow must be circular. The authors prove a stronger version of this conjecture, assuming a unique stagnation point within the domain. The proof involves defining a stream function, using the tangency condition and the uniqueness of the critical point to establish a semilinear elliptic boundary value problem. By applying propositions, they show the stream function is locally symmetric and radially decreasing with respect to the origin, thus proving their version of the conjecture. This work contributes to understanding fluid flows and their stagnation points, providing insights into two-dimensional incompressible fluids under certain conditions. The proof of the Liouville theorem for the Euler equations in a disk relies on two auxiliary results. The first, proposition 3.1, states that the stream function of a steady flow satisfies a semilinear elliptic equation under specific assumptions. This is demonstrated by considering any point y in the disk D and its associated solution sigma y, which is of class C1 and ranges in D, Z. The function g, defined as the composition of U with sigma y, is an increasing homeomorphism from t, y, t plus y, onto 0, u, z. The function f, 0, u, z, right-pointing arrow r, defined by equation 3.3, is of class C1 and satisfies delta u plus f, u, equals 0 along the curve sigma y, t plus y. This equation's validity throughout D is shown by considering any point x in D and its associated periodic solution xi x. The streamline phi x is a C1 Jordan curve surrounding Z in D and meets the curve sigma y, t plus y, once. Since both the stream function u and the vorticity delta u are constant along the streamline phi x, it follows that delta u, x, plus f, u, x, equals 0. Consequently, delta u plus f, u, equals 0 in D. The continuity of u in D ensures that min t element of R, xi x, t, right-pointing arrow R as x, right-pointing arrow R and max t element of R, xi x, t, z, right-pointing arrow 0 as xz, right-pointing arrow 0. The proof establishes that increment u is constant on partial differential D, denoted as D, and sets f, 0, equals D and f, u, z, equals increment u, z. From equations 3.2 and 3.3, it infers that f is continuous in 0, u, z, and the equation increment u plus f, u, equals 0 holds in D, thus completing the proof. The research also presents a result on the symmetry of solutions to semilinear elliptic equations with a continuous nonlinearity in a ball, based on continuous Steiner symmetrization. Specifically, proposition 3.2 states that if U is a weak solution to the problem increment U equals f, x, u, in a ball BR, with U greater than 0 in BR and U equals 0 on partial differential BR, then U is locally symmetric, decomposing into disjoint sets AC, where U, x, equals UK, xzk, for x in AC, with UK being a decreasing function in RK. The application of Liouville's theorem to the Euler equations in a disk is a significant area of research, building upon works by Constantin, Drieves, and Ginzburg, as well as Hamel and Nadirashvili. This field is crucial for understanding fluid motion and the properties of steady flows. Symmetry and uniform rotation play key roles in fluid dynamics, particularly in the context of elliptic equations in unbounded domains. Shear flows and parallel flows are also essential for comprehending fluid behavior. The discussion is dense with technical terms and mathematical concepts, reflecting the complexity and depth of the research in this area.